Alright guys, we are now actually doing these videos from my house. And as you can see, I no longer have a massive whiteboard in front of me. In fact, actually at Chat State in my lecture room and lab, I have 3 whiteboards that I can work with. So the other day we were told that you were going home and you were not coming back. So I went renegade and, well, it was with approval, so I guess not renegade, and snagged a whiteboard so that we can actually continue doing these lectures and see if we can keep some efficiency. So the last lecture that we had, we talked about the resistive capacitive circuit, well, an introduction to capacitors, and then actually the interconnection and the derivation of the solution to the differential equation. So what we're going to do is look at a couple of examples on how to actually perform this analysis, essentially without Laplace transform techniques. And that's why we derived everything from the time domain the other day. And what we have here is basically, once again, resistive capacitive, meaning that there's only one energy storing element within the circuit. Therefore, we have a resulting first order differential equation in which essentially we only have one root to the exponential form of that solution. Now, 3 things that we're constantly looking for within these types of circuits is finding the initial condition, looking at the final condition, in which both of which are the initial steady state and then the final steady state solution to the voltage across that capacitor. But then we were looking for the time response, which is essentially resultant as the exponential portion of that solution. If we go back to the form of the solution of the differential equation, Vc of t is actually equal to V infinity, which is the final solution, and then plus Vc naught, the initial condition, minus the final condition, and that forms actually the coefficient for that exponential portion. So essentially on this problem, what we had was basically a 24 volt source that provided an initial voltage across this capacitor in steady state. And then at t equals 0, and remember at t equals 0, that's when we actually change the schematic essentially. And by changing the schematic, we invoke a change for the voltage across that capacitor. So here at t equals 0, the switch maneuvers from the left-hand side over to the right, which essentially disconnects the 3K ohm resistor, the 5K ohm resistor, and the 24 volt source, and then connects that capacitor to the 4K and the 30 volt source here. And so essentially what we're going to see, and I just want to look at basically the timeline here, is that we start off with an initial condition for t less than 0. Remember, t less than 0 is where we find our initial condition. That's when we have steady state before we invoke that change. At t equals 0, we flip the switch, we change basically the resistance and the voltage sources within the circuit. We go through an exponential rise in which we actually regain into a steady state condition in which we have a new voltage across that capacitor. So usually what I have students do, because both parts of these processes, there's 3 parts obviously we're looking for 2 steady state conditions, and also essentially the time constant tau, which is for resistive capacitive circuits, just equal to RC. And that is actually what we use within the exponential. And what we later on see in circuits too is essentially a portion of the root of the solution to that differential equation. But I always tell students to go ahead and look at the two steady state conditions first, because they're basically the same processes. We're finding an initial voltage across the capacitor. We're finding a final voltage that's actually being done across the capacitor. Now, as a reminder, for these circuits here, especially with the capacitor, that IC of t is equal to C dVt dt. That is our current voltage characteristic for the capacitor, meaning that the current is dependent upon the capacitive value multiplied by that change in that voltage. So that current's dependent upon that change in that voltage. As long as we have change in that voltage, we have current. If we don't have change, we have no current, and that's when we model, when we don't have change, that's steady state. And that's when we model that capacitor as an open circuit. So let's take a look here. Remember, IC of t is equal to is dependent upon that change in that voltage. So the voltage can't instantaneously change, but the current can. Let's look at our steady state values here. So for t less than 0, here we basically had a voltage source, the switch was connected over. Our capacitor is sitting in steady state, so we have an open circuit here. Now just because that's an open circuit doesn't mean that it can't have a voltage across it. Because that capacitor is actually connected in parallel to the 5K ohm resistor, we would actually find that initial voltage for that capacitor across this 5K ohm resistor. And so right side of the circuit's completely disconnected. We're not even working with that. So right here, guys, all we have to do is, because that capacitor is sitting in parallel with this 5K ohm resistor here, we've essentially have a series circuit. No current can flow past that 5K ohm resistor, so it goes right through and cycles right back to the source. So here we actually can just simply perform voltage division in order to find the voltage across that 5K ohm resistor. So V naught, the initial condition, is equal to 24 multiplied by 5K over 3K plus 5K, in which that gives us a value of 15 volts. Now, for the final condition, we're going to look at the exponential portion in just a bit, but for the final condition, we signify that as t equals infinity. And all infinity means, guys, is that the circuit has been sitting there after the switch has switched over, after the event has occurred in which it goes through a change. It's been sitting there for long enough to regain a steady state again. It's kind of like chaos theory in some way. If anybody knows anything about entropy, essentially if you create chaos, essentially the natural order of things is that once chaos has been formed, basically things want to resettle back into order. Usually you have order to disorder and then reorder. Same thing here, is that we create a change, things want to regain that steady value. And so what happens at t equals 0 is that we threw that switch over, went through the transient period, and then at t equals infinity, we regain basically another steady state condition. And what we see right here at t equals infinity, here we got 24 volts and 3K and that 5K, once that switch moved over, that's fully disconnected. That capacitor is no longer connected to any part of that left portion of the circuit here. And so circuit went through steady state, went through the transient period and regained its steady state. And now that capacitor is still connected to the 4K and the 30 volt source. Essentially what we have here though, guys, is we have a full open circuit. Now, because we have a full open circuit, that doesn't mean that capacitor is not connected to that 30 volt source. It is still connected to the 30 volt source, but as we said, that current is dependent upon that change in voltage. So because it's once again acting in steady state and modeled as an open circuit, then essentially what we have here is no current flowing through this section of the circuit. So what we have is no current flowing through that 4K ohm resistor. Because no current's flowing through that 4K ohm resistor, there's no work being done, therefore no voltage is actually being applied across that element. Therefore, that voltage, that final voltage across that capacitor is actually just equal to 30 volts. So, initial voltage for the capacitor was 15 volts, and then the final voltage was 30 volts, and so then we go through, look at the transient period, because the transient period basically is where we see that change, that exponential change is happening. Now, in the prior video, we looked at an exponential decay. We're looking at basically an exponential rise. We're going from 15 volts to 30. Let's take a look at how to determine basically the time constant, tau, for this resistive capacitive circuit. Now, we derived this the other day, in which tau was equal to R Thevenin times C. If you watch the Thevenin equivalent circuit, I say R Thevenin because it's the same process that we do in order to find basically the Thevenin resistance within a circuit. We turn off all sources and then we equate that resistance to that capacitor because it's the resistance that the capacitor sees that drives that response, that really drives the exponential portion. So if we take a look here, tau is equal to R Thevenin times C. And so if we turn off the voltage source, remember we turn off the voltage source, goes to 0 volts. So then as soon as that voltage goes to 0, it acts like a short circuit. I'm misasking you guys these questions. But essentially that causes 4K to become in parallel with that capacitor. So essentially we're personifying ourselves as that capacitor, and we're looking into the circuit here. And that capacitor is looking into the circuit. What resistance does it see? And that 4K is actually all the resistance that's actually going to be seen by that capacitor. If we had two elements in series, it would be those elements together. If we had an element that was in parallel with that 4K, then those would be in parallel. We're just equating resistance naturally to an element, just like we did in terms of equating that resistance to a source back in chapter 2. So tau here was equal to 4K and then multiplied by its capacitive value, which was 0.05 millifarads. So that's 0.05 times 10 to the negative third. When we multiply these two together, we actually get a value of 0.2 seconds. And if we look down here, Vc of t is equal to Vc infinity. That's a scalar value here. That's the final value. Added on to the transient portion, which is an exponential, but the coefficient for that exponential is Vc naught minus Vc infinity, or the initial condition, and then we have the final condition subtracted off, and that forms basically 15 minus 30, which gives us negative 15. And then in the argument of the exponential, we have negative t divided by 0.2, so we get 30 minus 15 times e to the negative 15 times t volts. So this is our full and what we call the total response. Every portion of this, t less than 0, t greater than 0, t equals infinity, we can easily go through and calculate whatever value we want over time that models the true response, the total response for this circuit. So for the voltage across that capacitor specifically. But just make sure that you understand that Vc naught minus Vc infinity, you have to subtract off that final condition from that initial condition to give the true coefficient here. That is multiplied by the exponential. All right, so next problem we're probably going to look at is just another example, and due to the nature of how much space I have, we're just going to continue going on example by example by example. So these will be individual, they will be posted on eLearn. Can look through the YouTube website as much as you want. I think we're going to start looking at the resistive inductive circuits next. See you then.